I wanted to start by thanking you for inviting me to your meeting. And I always love coming to Chile. And the next best thing is to see you on the Zoom. But anyway, I have many friends there, and I hope that some of you are there this morning. And I look forward to seeing you again in person one day soon. So look, I thought that today, rather than try to cover the whole of artificial intelligence in the anterior segment of the eye, I would do something that's a little bit more direct and relevant to everybody. And if I am not coming over clearly in English, if I'm not being understood, then you can tell me and I will try to say something in Spanish. You can interrupt me, okay? So we're going to concentrate on biometry in the short time we have, because that is an area that is important to all of you. And I'm going to touch on how I think it's going to change and how it's already changing. So let's see. So where we are with biometry is not quite where we are with laser vision correction. In laser vision correction now, the standard is about 90% of people within half a spectacle unit of the target refraction spherical equivalent. In the lens work, in the IOL implants, even with the best formulae, it's only about 80%, just over 80% these days. So we clearly have room for improvement. There is a space to make it better, even now. And so what am I doing in biometry? Well, I can tell you what I was doing and what I think we were all doing until quite recently. I was using SRKT for the normal eyes and then half a Q for the short eyes. And we were aiming a little bit myopic in the long eyes, and again aiming a little bit myopic in the very high powers as well. So at both ends of the spectrum. This is because the formulae were regression formulae, just based on axial length, really, and the straight line of the linear regression had a curve at either end of the spectrum, so you had to go a little bit myopic. So conventional biometry formulae that we all remember well, we all grew up with, they were all based on simple linear regression. And what they're trying to do, I don't know if you can see this box on the right, and I'm not sure if you can see my pointer there. Maybe I've got some kind of tool here. Let me try that. And I'll try the highlighter, laser pointer here. Let's see. I hope you can see that.
We see it.
Oh, great. Okay.
Yeah.
So look, here is the standard sort of biometry image readout, cross-section. And you can see that the old formula we were using, we're trying to estimate the lens position in the eye after implantation using axial length and linear regression and the K values. And reasonably accurate. You can do better. Wolfgang Hages looked at the anterior chamber depth too and changed that to a multiple linear regression model, but there are limits to the accuracy. And so most of us now have moved on a little bit, and this is what I'm doing now. I'm on the Kane calculator. I find the Kane formulator, well, extremely easy to use. The difficulty with most of the internet calculators now is that they don't have automated export of the data. So many of you will use one of the contemporary calculators that is built into your biometry machine. For example, the IOL 700 has the Barrett formula built into it, and you can use those. I think the LensStar has the Olsen formula, which isn't bad either. But if you look at comparisons, then the Kane formula is very near the front, and it's a very easy online calculator to use. And it also does the toric calculation for you. So I find that a good one to go to. For the non-toric lenses, there's a very interesting thing being done by ESCRS, which we'll talk about in a bit. And that is a web scraping device that gives you a comparison between all the different leading formulae. And it already works well for non-toric lenses, but it doesn't yet work for the torics. And neither of these formulae work for the post-refractive cases. So I'm still using Hages L post-refractive, and it's okay, but it's not perfect. And we're always checking the lens constants using customized constants, and the site to go to for that is iolcon.org, and that gives you the contemporary lens constants. if you're not using a lens that's already in the list in your calculator, you're using like the K. So that's what I'm doing right now. I've just been calculating some lenses earlier this morning, and there's the formula that I used. So if you look at a head-to-head of the current formulae, see which one is doing best. It slightly depends on the comparison you look at. This one in ophthalmology put Kane at the top, but you can see that Olsen and Barrett are very close. And Hill RBF, I think, has improved recently, and all these formulae to the left here are all doing quite well, getting just over 80% plus or minus 0.5. But you can see the older formulae are not doing so well. So choose one of the formulae at this end, and I think these three are pretty good. Here is the Kane formula calculator, just to show you how easy it is to use. But the problem with all these calculators is that you have to type the data in. So there's a potential for making a mistake, which is never good. So be careful when you check. And I think soon we will be able to export the data automatically. There are ways of scanning PDF and machine reading into these websites, and I'm hoping they will incorporate that soon so that we can't make the mistakes. So who is using artificial intelligence in the lens formulae? So a version of that is being done by three of the leading formulae. That's Damien Gatinel's Pearl DGS formula. He has a very good clear explanation of how that formula is derived, unlike the other formulae in one of the papers that you can look up there. And then Jack Kane, he's remarkable. He did this work as a registrar or an ophthalmologist in training, which you have to admire. And then there's Warren Hill, who's been working in this space for many years. And they all use tabulated data and machine learning to help them to predict the lens position in the eye after implantation, which is the main thing we don't know, which is the, if you remember that first biometry section, where the intraocular lens is positioned along the axis of the eye. That's the main area of uncertainty. And if we could predict that accurately, then we can get much more accurate refraction outcomes because everything else is known. So these three formulae all incorporate a form of machine learning based on tabulated data to improve the prediction of the position of the intraocular lens in the eye after surgery. So how are we going to improve on what they are doing? Well, the easy bit in machine learning is actually doing the analyses. The difficult bit is collecting good data sets. And there are some areas where we can improve in anterior segment surgery by just doing that, by collecting data in the right way. And here are some areas we are attempting to improve in Moorfields. Keratoconus, we are quite far advanced with. The other areas we need to continue working. Our data collection is not yet perfect. And you could add infection to that list as well. We're looking now at standardizing our imaging protocols in infection too. And so you collect this data from a fixed sequence of scans according to a protocol, and you collect the data in your electronic healthcare record system. And if you do that, the data quality starts to look very like the data you're collecting in clinical trials. It's collected in electronic archive, and you're collecting the data according to a protocol. So this is high quality data, but it's collected in routine clinical care. This is what we're doing every day for all our patients. We're collecting data according to a protocol. And that's what we call protocol-driven care. And it has some real advantages for subsequent research. First of all, if you look at data protection laws in Europe, that's the General Data Protection Regulation, and a similar framework is there in most countries now. De-identified healthcare data, in other words, healthcare data with the personal information removed, you can use that for research. And if the data is collected in the course of routine clinical care, you don't need any special measures for consent. or IRB approval, so ethical review. You can just go ahead and do the analysis on anonymized data, data with the personal information removed that you collect in the course of routine clinical care. So that makes research a lot more easy to do and a lot less expensive than it would be otherwise. And so this is very much the direction in which healthcare is moving. That's towards protocol-driven care. So we hope to collect data sets of a size that will help us to do machine learning studies. And that's about 1,000 to 100,000 eyes, somewhere in that area. So larger than the data sets that are normally used in clinical trials. And also we're collecting image data where we can. And using the image data with labels. And what do I mean by that? And that's when you have an image, it's meaningless unless you can say what the image is. So you need to have an idea of what the image is showing, how it was derived, and as much descriptive information, the age of the patient, the gender, the other information about their healthcare status, the drugs they're on. This is all collected in a routine clinical care. It's all collected in the electronic record. And so what we're trying to do at Moorfields is to put that data all in the cloud together with the images. And that's going to enable us to do the really interesting analyses. And there's one particular branch of artificial intelligence and machine learning that is worth you being aware of, and that's called deep learning. Now, what is that? Here's the classic illustration here. And deep learning is, remember when a computer is looking at an image, it's not looking at an image, at least we don't think it is unless they're conscious. It's really looking at a set of numbers. And in much the same way as sets of numbers are broken into patterns by Fourier analysis, for example, or Zernica analysis in wavefront analysis, you have an array of mathematical functions that first of all collect data on the lower dimensions. And the analogy I'm using here is wavefront analysis. You filter out the tilt, the cylinder, and the sphere, and then you go on to the higher orders, which would be, for example, in the third order, it would be trefoil and coma. Then you've got the fourth order, which would be spherical aberration, pentafoil, and the other terms. And each time each of these mathematical functions filters out the amount of each of these areas of defocus, and you're left with just the tiny amounts in the higher dimensions that you're looking at with these other functions here. So these are arrays of mathematical functions arranged a bit like the human brain. That's what a deep learning model is. And the way they work is you can present them with image data, is one thing that deep learning is very good at. It doesn't have to be image data. It can be tabulated data or image data and tabulated data, so-called multimodal data. And you present that data to the computer and you give it a label. And you say, all these images here are cats in the example here, and other images are not cats. And you train the model using labeled data. In other words, the computer knows what it is. And then from that, it learns how to tell what an image is showing, and whether it's showing an image of a cat or not a cat, or an image of keratoconus or not keratoconus. You're looking at the cornea. And it can also do linear predictions as well. And so it's really exciting, and it can do some rather incredible things. If we're looking at the retina, which is where most of the work has been done so far, you can tell someone's age within 3 years just from a fundus photograph. You can predict their gender with almost 100% accuracy just from a fundus photograph. So it can do things that you and I can't do. And it can predict cardiovascular risk from a retinal photograph. It can predict within reasonable accuracy your blood pressure, your body mass index, your hemoglobin A1C, and these indicators of cardiovascular risk. It outperforms trained specialists in sorting retinal disease, and in also sorting, sorry, my secretary's just come in here, Angelique, my practice manager. And so it can do some surprising things. So it can perform tasks that we're asking doctors to do routinely, more accurately, more repeatably than doctors can. And it can predict risk in certain eye diseases. And most recently, we've had the team of Moorfields who are looking at this in a collaboration with Google DeepMind. They've been looking at some neurological diseases, and you can predict Parkinson's disease 7 years in advance of the onset of clinical symptoms. And this opens the pathway to routine screening in the population generally, because it's much cheaper than doing a brain scan to do an OCT of the retina or a simple retinal image like this. It's much cheaper to do that than it is to give everyone a brain scan. And it becomes much more practical to talk about screening the whole population then, and then perhaps intercepting these diseases with new drugs like Alzheimer's before people are too badly affected by them. And so this is the way medicine is going, and it's really exciting. And that's why I think it's helpful to understand deep learning. So the paradigm is simple. You just collect the data in routine clinical practice, and then you divide that data into a training data set. You usually take about 80% of the data, and you train your deep learning model on that data, develop a new algorithm for making your predictions or your classifications. And then you test how well the computer is doing with the new model on a data set that it hasn't seen before. And that's called a validation data set. And then if it looks good, then you're ready to apply it in routine clinical practice. You may think, oh, well, you have to be a computer expert to do this. Well, you don't anymore, because the computers themselves will make a suggestion of the right model for you to use. And so it's like asking ChatGPT. You say, how am I going to analyze this data? And it will tell you. And so if you want to visit Google Auto ML, you can see how well that works. And in a study done by my colleague Piers Keane here at Moorfields, he's a great enthusiast in this area, he showed that even medical students and junior doctors could outperform computer experts in training a new algorithm for recognizing retinal disease. And so you can do it. You just need the right data. And so in terms of biometry, what are we going to do? We need the biometry images, of course. We need the IOL information, and we need accurate refraction data to improve on what Jack Kane, Warren Hill, and Damien Gatinel have already done. And ideally, you need pre- and post-operative images showing you where the lens position actually ends up after surgery to train a deep learning model. And so to collect the image, the lens information accurately, there are barcodes in every lens box, and ideally we need a system for scanning the barcodes into our electronic healthcare records, so we have all the information about the lens. The more information or more richly labeled the image data is, the more accurately the machine learning can work for you. And in terms of refraction, which is often the weak area after cataract surgery, autorefraction is reasonably okay, but it's quick to do, but it's less accurate than subjective refraction, but that's very slow to do. But there are newer forms of subjective refraction that are a compromise really between autorefraction speed and subjective refraction's accuracy. So this is something called direct subjective refraction we saw at ARVO recently, and that looks very good to me. It's much faster than manifest refraction, and it's about 4 times as accurate. So it's a really exciting way of looking at sphere and cylinder after cataract surgery. And so the more accurate your labeling, the better your deep learning models become. And so in doing that, I think we can make all the right predictions about what we're going to do with our biometry. And then if we want to look at which lenses are performing best, we need to add binocular visual acuity data. Most of us are still testing the data monocularly. You need to use a semi-automated method for that, and we need the right patient-reported outcome measures as well. And so if you're still using Snellen charts, it's time to abandon them. use logMAR charts at least, and look at a semi-automated way of measuring visual acuity. We do this routinely in the refractive service in Moorfields now. It's easy to do and it's quick. And then with regard to the patient-reported outcome measures, we've done some work on this and developed something called the VCQ, which we hope is psychometrically robust. It's very quick to do. It's something the patients can administer to themselves on a phone or on an iPad. And the data is self-scoring and self-archiving. And we are working on a standard data presentation for it now, so it's easy to use. We're trying to develop an app for it, so that's free to download and easy to use. You can look that work up here. And so that's the ideal cataract clinic pathway. Remember, if we're going to do deep learning and improve our biometry formally and select the right lenses and learn to do the medicine better, we have to do protocol-driven clinical care. And this is the protocol that you need in your cataract clinic. You do the biometry. I think in reference centers, there's a case for doing the biometry pre and post-surgery. So you're imaging the final lens position, and then we can learn from it. And then we're collecting all the IOL information by using barcode scanning in theater. That's the aim. We're using an accurate form of refraction measurement, binocular acuities, and we're also asking the patients how they feel after surgery about their visual quality and the effect on their quality of life. So at ESCRS, we're trying to encourage this kind of research. So I want you to keep your eye on the ESCRS webpage. I think there'll be a round of the Digital Research Awards coming soon again. And if you have good data already that you're ready to share and make it public, or you know how you have a method for improving your data collection, then this is the kind of work we want to sponsor. And so keep your eyes on the webpage, and I hope you're going to get excited by this and want to participate in it. And so there they are, the Digital Research Awards, and you can read about those on the ESCRS webpage.